Alright, so we'd like to thank you for this chance we have to present our simulation project, and we chose to optimize the time it would take for a space shuttle to travel from the Earth's surface to the Moon's surface. And being seniors in chemical engineering, we've had a lot of experience with physics and engineering problems in which we'd have to derive force balances and do simulations, so we feel qualified to take on this project. And we understand that one of your concerns might be how realistic or accurate our model was able to be, and how comparable the results of this optimization would be to data provided by NASA and other actual space voyages. So our objective here is to address those concerns and to display the findings that we had in our project. So without further ado, we'd like to begin our presentation. So displayed on this slide are the parameters that we used for the simulation. These values were based off of literature values, and the design problem was, what is the minimum time for a space shuttle to travel from Earth to the surface of the Moon? And this optimization was subject to certain constraints, being that we could not exceed a given amount of mass for the fuel that was provided, and also the space shuttle would have to reach a velocity of 0 once its position was at the surface of the Moon. So this means it would decelerate and arrive at 0 so that it could safely land without crashing while still making it the full distance to the Moon.
Great. And as Dylan just showed on the previous slide, he showed a table with the parameters and the variables. But I want to focus your attention to the equations, specifically the second equation. And the second equation, that's a force balance on the space shuttle. And so we took into account, of course, the gravitational pull due to the Earth and due to the Moon. And then we also have a term here. This shows how the burn rate, so our fuel, and how it affects the forward and reverse propulsion. We have a variable there called INTV, and that was just simply a binary variable we used. And when it's positive, it means that the shuttle's forward thrusting, and when it's negative, it means it's reverse thrusting. And then the last term here is just the drag force. And again, we also used another variable there, W, and that activated whether or not it was turned on or off. So when the drag force, or I guess when we're going through the atmosphere, drag force is not negligible. You got to take that into account. But once you go into space, there is no drag force. So W would be 0 when you're in space. And then our assumptions. We assumed 1D travel, as you could tell from the equation. We assumed constant space shuttle mass. We just assumed that the burn rate does not exceed 100 kilograms per second, and that's what we found to be pretty standard in our best case. And then the forward thrust was used for the first half of the voyage, reverse for the second half, and that was simply to help the optimizer to come up with a good solution. And then here is a plot of our best fit trial and error without the use of an optimizer. So this was just us manually changing the code and the parameters. And so as you can see, the top curve here, this is the velocity curve. We were able to successfully minimize it, but we were not able to reach the surface of the Moon, as seen by the second plot. And the third plot, we used too much fuel. So, and that was the same case as in all of them. We could only meet one constraint. The other two constraints were unmet. And that's why an optimizer had to be used for this project.
Okay, so this is the plots showing our best fit optimized solution. So Ben showed us when we did manual changes what happened. We weren't able to meet all the constraints. So with this one we were able to meet all the constraints. I'd like to focus first on the first and third plots here. So with the third plot, you can see initially there's a large initial forward thrust up to about 50 kilograms per second, which causes a large initial acceleration, which allows the space shuttle to escape the Earth's atmosphere. And then afterwards there is a constant cruising velocity. And what this does is, so basically it has a large initial acceleration followed by this cruising velocity, and then a large deceleration that is caused by a large, so there's this deceleration, and then that's caused by this right here. So the mass of the spaceship also did not go below the constraint, so it used only the amount of fuel that we told it it could use. As well, the spaceship actually reached the surface of the Moon, so that constraint was met as well. Just to conclude, the optimum solution started with a large initial thrust followed by an optimum cruising velocity, and finally there was a large dethrust which allowed the shuttle to approach the surface of the Moon. As you saw, the model provided an optimum time travel of about 5 days, and this is pretty close to the average time provided by NASA of 4 days. And lastly, we also focus on drag force. So if you look at the graph to the right, there's plots of drag force and no drag force. And as you can see, the overall time to get to the moon was not really affected by drag force, but the velocities throughout the travel were changed a little bit. And that's it.